Assalamualaikum and hi everyone. Today, our group will be presenting our group assignment for BERT 3373 Digital Signal Processing course. Lecture by Madam Izadora binti Mustaffa. Our assignment title is Windowing Filter. Before we dive in, let me introduce our team members. Me, Nurulain Sofea binti Hisham. Next, Aieenna Illeeya binti Nurzana. Muhammad Razmer Ar-Ridzwan bin Muhammad Rosli. Muhammad Faiz Adni bin Muhammad Yusri. And Muhammad Iskandar bin Dzulqarnain bin Ibrahim. Our presentation is structured into 9 main sessions. We will begin with an introduction and our objective, followed by the theory and the definition for both windows that we will choose. Then, we will look at the characteristic, design method, and real-world application for that two windows that we choose. Finally, we will wrap up with a discussion and conclusion. For this assignment, we need to select two windowing filters. So, we will select Humming window filter and Kaiser window filter for our main filter for this presentation.
Assalamualaikum everyone. My name is Muhammad Faiz Adni bin Muhammad Yusri. My matric number is B12241041. So today we are diving into a fundamental concept in digital signal processing, which is a window filter. It also known as a window function. So at its simplest, a window function is a mathematical curve that use a shape as a signal. Think of it like a camera lens shutter. In the theoretical world, signal can go on forever, but our computer have limited memory and processing power. So we can't look at everything at once. So we have to isolate a specific segment of the data to analyze it. That's what a window filter does. It defines the boundaries of what we are looking at. Now, why can't we just chop the signal whatever we want? So in the real world, if you take a infinite signal and just cut it off abruptly, so that's what we call a rectangular window. So you will create a sharp edge at the start and at the finish. To a computer performing frequency analysis, those sharp edges will look like a high frequency noise that wasn't actually there. So this is known as a spectral leakage. It's like trying to listening a song, but someone is constantly clicking a mute button on and off. So that clicking sounds will distortion the actual music you are trying to hear. Instead of a hard cut, we use a window that smoothly taper the signal to zero at the edge. So by gradually fading the signal in and out at the boundaries, we make the data appear continuous and periodic. So this prevent the distortion that I mentioned earlier. So it cleans up the data and allowing for a much more accurate frequency analysis. Whatever you are analyzing, audio, radar, or medical imaging windowing, that ensure the frequency you see in the result are the frequency that actually exists in the signal. So to summarize is, windowing is our way to translating infinite theoretical data into finite management and most importantly, accurate digital information. It minimizes distortion and maximizes the clarity. Moving into our core objective, our primary goal is to minimize spectral leakage. As we touched on earlier, we truncate a signal, so we create artificial discontinuities by using windowing function to smoothly taper the signal zero at the edge, so we reduce those unwanted frequency by ensuring our digital representation stay true to the original source. So our second objective is arguably the most critical for design, which is controlling the trade-off between the main lobe and the side lobe. So the main lobe width is vital because it determines our frequency's resolution. Essentially, how we can distinguish between two close frequency. So on other hand, the side lobe level determine our dynamic range or amplitude accuracy. So in engineering, you rarely get the both perfectly. So if you narrow the main lobe to get better resolution, your side lobe often grow, potentially hiding a smaller signal. So finding the right balance for your specific data is the key. Thirdly, we are going to analyze the characteristic of two specific window, which is the Hamming and Kaiser window. So the Hamming window is what we call a fixed parameter window. So it's a reliable set it and forget it choice for general use. However, the Kaiser window is an adjustable parameter window. This gives us much more flexibility and allowing us to tune the window to prioritize either resolution or dynamic range depending on our needs. Finally, we want to grounding all of this in real-world application. These filters aren't just theoretical maths, they are also the backbone of audio processing like noise cancellation in our headphone. Next, communication system that ensure clear data transmission over cellular network and high-tech engineering and medical field, such as refining the imagery in MRI scan or a radar system. So by the end of this session, you all will understand how to select and apply the right window to solve this real-world challenge.
Assalamualaikum, my name is Nurulain Hisham and my matrix number is B1224104474. Today, I will present about the theory behind our assignment. When we design an FRL filter, we usually start with what we call an ideal frequency response. This ideal response is mathematically infinite in time, meaning it has an infinite impulse response. Because computer and hardware have limited memory and processing power, we cannot implement an infinite signal directly into a system. So, we apply a method called windowing. Windowing allows us to cut that infinite response into a finite one that the hardware can actually handle. This process also helps us shape the frequency response to meet our needs. However, cutting a signal is not perfect. It can lead to two main issues, one spectral leakage and second to the Gibbs phenomena. To manage this issue, we choose different window function based on specific trade-off. First, Hamming window is a provide a good balance, offering moderate side loop attenuation with solid frequency resolution. Second, Kaiser window is more flexible, giving us adjustable control over side loop level and transition bandwidth.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurulain binti Nurzana. My metric number is B1224104478. Today I want to explain definition of window filter. There are two types of window filter. Number one is Hamming window and number two is Kaiser window. Okay, the first one is Hamming window. To begin with a definition, a Hamming window can be considered as a mathematical function through which the tapering of edge of a particular signal segment are accomplished. Next, we ask ourselves, why do we need to do all of this in the first place? Moreover, we are forced to solve the problem commonly known as rectangular windowing. Now, when you arbitrarily reduce a signal to analyze it, this square cut boundaries inside the signal from something called spectral leakage. It is like pony noise in your data, whichever existed in the first place. The solution is the Hamming window. Through this function, we round off the beginning and end our data segment. This rounding off step has improved our frequency accuracy by eliminating this mathematical stepness. As the final point, if our examine the visual ideal slide, it is possible to see that a comparison might be made between one of side a square cut of signal harash edge and on the other side a rounded Hamming signal that is much more natural and ready to a close analysis. So for the next is where is Hamming window used? Now that we understand how it's work, let's look at where we actually use in the real world. First, it is standard in the speech processing. It's used in everything from your phone system to AI voice recognition to help analyze complex human speech pattern. Secondly, it is important for both radar and sonar. Since the Hamming windows move signal so well, it's helped engineer find small object or weak signal which might see right next to much larger object or strong signal. For the third one, it is a basic tool in digital filter design within the design of finite impulse response or FIR filter. In short, every time a messy, real-world noise must be converted into clear digital data, the Hamming window is one of our most reliable tools. Next, we have a Kaiser window, which we often call the Swiss Army knife of windows. It is highly adjustable, unlike the fixed Hamming or hand. The key here is the shape parameter. Using one of number of engineer can control just exactly the shape of the window. This is because a perfect thread of between precision, which is our frequency resolution and noise reduction, which speak for side loop, levels can be achieved. Why do we pros use it? Because it is the standard of the industry when a filter design has to have very strict mathematical requirement. For example, when a project requires that noise must be exactly at negative 16 dB of the signal, then the Kaiser window is the tools that allow us to tune the filter to each exactly that goals. Let's compare these two directly to see which one is fit for our project. A Hamming window is considered to be a type fixed, simple, with laser CPU requirement. Its side loop level is always fixed at negative 43 dB, thus making it the best for rapid calculation such as voice analysis. For the Kaiser window, it's also adjustable and has a much better and more complex calculation, but it is possible to define a side loop level between negative 40 and negative 100 dB. Thus, it is by far the winner when it comes to high performance. Finally, if you want to speed and ease of use, we use Hamming. But if we require unlimited control with precision, we use Kaiser.
Hi, my name is Mohd Razmer Ar-Ridzwan bin Mohd Rosli and my matric number is B122410482. Today I will explain the characteristic of Hamming window filter, the MATLAB code, the flowchart, the output. This slide explains the characteristic of the Hamming window filter. Basically, it's used in signal processing to make the frequency result cleaner. First, it has good side loop attenuation, meaning it can reduce the side lobes in the frequency response. So unwanted frequency component becomes smaller and there less interference. Second, the thread is produce a wider main lobe. This means the frequency resolution is not as sharp compared to some other windows, but we get better noise suppression. Third, it helps to reduce spectral leakage. This happens when the signal energy spread into nearby frequency and the Hamming windows moves the edge to reduce that effect. So overall, Hamming window is popular because it gives a good balance, less leakage and less unwanted noise. Even though the main lobe becomes slightly wider. This slide shows the MATLAB code used to implement the Hamming window filter. First, the code generates the Hamming window and creates a sample sinusoidal signal. Then, the window is applied to the signal using element-wise multiplication. After that, FFT is performed on both the original signal and the window signal. This allows us to compare their frequency responses. The main purpose of this code is to show how the Hamming window affects the signal in both time and frequency domain. This flowchart illustrates the overall process of implementing the Hamming window filter in a clear and structured way. The process starts by analyzing the MATLAB environment to ensure all previous data is clear before running the program. Next, the window length is set to n equal to 50, which defines the number of samples used in the analysis. After that, the Hamming window is generated, followed by the creation of a sinusoidal input signal. Once both the window and the signal are ready, The humming window is applied to the signal using element-wise multiplication, which helps to smooth the signal edge in the time domain. The time domain signal are then plotted to visually compare the original and window signals. Next, the FFT length is defined to obtain a smoother frequency spectrum, and FFT is computed for both signals. Finally, the FFT results are plotted and compared, allowing us to observe the reduction in spectral leakage caused by the humming window, and this marks the end of the process. This graph shows the humming window in the time domain, where the amplitude is maximum at the center and gradually decreases toward the beginning and the ending of the window. This move shape is important because it avoids sudden changes at the signal boundaries. By reducing sharp edges, the humming window helps to minimize discontinuous when the signal is transformed into the frequency domain. As a result, this window shape plays a key role in reducing spectral leakage during frequency analysis. This slide compares the original sinusoidal signal with the humming window signal in the time domain. We can observe that the original signal has a constant amplitude throughout the samples, while the window signal shows reduced amplitude near the start and the ending. This reduction means the signal is mostly tapered instead of being abruptly cut off. By smoothing the edge of the signal, the humming window reduces sudden transition, which are one of the main causes of spectral leakage in signal processing. This graph shows the FFT comparison between the original signal and the humming window signal. We can see that the main frequency peaks are still clearly present in both signals, which means the important frequency information is preserved. However, the humming window signal has much lower side lobe compared to the original signal. Lower side lobe indicate reduced spectral leakage and less interference from nearby frequencies. Therefore, the frequency response of the window signal is cleaner and more accurate for analysis.
Now, I will present about the application of the humming window filter and why it's so important in practical signal processing. First, in audio processing, the humming window is commonly used with the fast Fourier transform or FFT. Its main role here is to reduce spectral leakage, which occurs when a signal is suddenly cut. By minimizing this effect, the humming window improves noise reduction, music equalization, and speed enhancement, resulting in clearly and more accurate audio signals. Next, in communication system, the humming window is used for channel filtering and interference suppression. It helps smooth the signal boundaries, which reduce unwanted frequency component that lead to better spectral analysis and more reliable data transmission, especially in bandwidth limited system. Finally, in engineering and medical field, the humming window has several critical applications. In ECG signal analysis, it helps doctors and researchers analyze heart signal more accurately. It also widely used in vibration analysis for fault detection in machine as well as in radar and sonar processing, where precise frequency analysis is essential for detecting and tracking objects.
Assalamualaikum. My name is Mohd Iskandar Dzulqarnain bin Ibrahim. My matrix number B122410512. Now I will present about the Kaiser window, which is a widely used windowing technique in digital signal processing. So for the characteristic of Kaiser window, the Kaiser window is unique because it has a flexible parameter called beta. Beta allows us to control three important characteristics of the window. First characteristic is side lobe attenuation. This determines how much unwanted frequency components are suppressed in the stop band. Second is main lobe weight. This affects the sharpness of the filter transition from pass band to stop band. And third is frequency resolution. A narrower main lobe allows us to distinguish closer frequency components, while a wider main lobe reduces resolution. So for the key trade-off for this characteristic, a larger beta value increase side lobe suppression, which is good for reducing interference, but it also widens the main lobe, reducing frequency resolution. Now let's move to the practical part, which is designing FIR filter using the Kaiser window in MATLAB. First, we define the sampling frequency, which represents how often the signal is sampled per second, and the cutoff frequency, which determines the highest frequency we want to pass through the filter. Next, we define the filter length, which impact how sharp the filter transition will be, and the beta value for the Kaiser window. After that, we normalize the cutoff frequency by dividing it by half of the sampling frequency. This normalization is necessary for MATLAB's FIR1 function. Then, we generate the Kaiser window with the chosen beta and filter length. This window shapes the filter coefficients to achieve the desired frequency characteristic. The FIR1 function combines the normalized cutoff frequency and the Kaiser window to produce the FIR filter coefficient. Finally, we use FREQZ to plot the frequency response, both magnitude and phase. The magnitude plot shows how well the filter pass or block frequencies, while the phase plot indicates signal distortion. Now, for the output of Kaiser window filter, for the first graph, show the Kaiser window in the time domain. You can see it rises smoothly in the middle and taper at the edge. This tapering is what reduces side lobe leakage in the frequency domain. For the second graph, show the magnitude response of the filter. The passband is nearly flat, which means the frequency we want to keep are preserved without distortion. The transition band is sharp and the stop band has very low magnitude, indicating unwanted frequency are effectively suppressed. For the third graph, show the phase response. The phase is almost linear across frequency, which is important for preserving the shape of signal, especially in audio or communication application. Now I will present about the flowchart to design the Kaiser window filter. First, we start the program and we define the filter spec, which is frequency sampling, cutoff frequency, the value of n and beta. And then we normalize cutoff using Wn equal Fc divided by half frequency sampling. After that, we generate Kaiser window using code W equal Kaiser and beta. After that, we design filter using code H equal FIR1 n minus 1 Wn W. After that, we analyze frequency response using the function FREQZ. And lastly, the output will be displayed on the MATLAB and program.
Finally, we want to consider a diverse array of application for the Kaiser window function and three major industry categories. In audio processing, it finds application in noise reduction, musical equalization, and speech enhancement. It is critical in communication system for channel filtering, signal reconstruction, and interference superposition. In engineering and medical application, it is employed to perform sensitive operations such as filtering and ECG signal, vibration analysis, and complex radar and sonar signal processing. For the discussion, the first point is the signal processing is a tug of war between resolution and leakage. If you want a super sharp frequency peak, you will generally have to accept more noise. If you want to super clean signal, the peak gets a little bother. We discuss the Hamming window as the reliable set to forget tools. It fits at negative 43 dB of noise superusation, which is good enough for most audio and speech tasks where we need speed and low CPU usage. But then, when we move on engineering and medical fields, good enough is not good enough. That is where the Kaiser window shine. Since it's tunable, that means engineer can dial in exactly what performing that one, sometimes pushing the noise down to negative 100 dB. Ultimately, it depends on what we are trying to do. Hamming if you want simplicity of or want it to sound good. Kaiser if you want needs precision for if it is mission or clinically important.
In conclusion, windowing filters are essential in digital signal processing to reduce spectral leakage and improve frequency accuracy when analyzing finite signal. The humming window is simple, reliable, and widely used in audio communication and medical application where efficiency and stable performance is needed. The Kaiser window with its adjustable beta parameter provide greater flexibility and precision, making it suitable for high-performance filter design. Overall, the humming window is ideal for general purpose use, while the Kaiser window is preferred when strict control over frequency, resolution, and noise suppression is required.